hosted by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Good afternoon, everybody. I hope everyone's having a wonderful day so far. I want to welcome you on to the stream. So just a couple of things I want to mention before I get into things. Let me just get this open just in case anybody's wanting to interact here. Just a couple of remarks. So the first thing I need to point out is that I am playing around with some somewhat new tech. So I've switched over the way I'm multi-streaming. So I'm using a different method for doing this. So just keep in mind that if there's any weird blips or anything, I'm hoping that we'll be able to catch those, or at least I'll be able to catch them. So if you see any weird things happening during the stream, just let me know in the chat. I would actually appreciate that. Furthermore, another thing to keep in mind is that, as per usual, if you would like to get the educational resources that are associated with the session, they'll be available on my Patreon at patreon.com/pagewizard. So you can find all the relevant links at pagewizardgames.com. So that means that everything that we're going to do here today, all the lessons, specific lessons, will be available afterwards. And also the stream will also be available afterwards. So if you say miss this when we're going live right now, as we speak, it's kind of meta, right? Like I'm addressing the stream as we're doing the stream right now. Anyways, we're going to be doing another session of Big O Bootcamp. And per usual, I think it's usually a good idea I lay out the definition of Big O before we get started, because I've already done in a previous installment of this series. I've already done a formal treatment of this topic, and I've also done lots of basic examples. We'll also be doing some basic examples here, but I'll be focusing instead on just Big O notation itself. So just keep in mind that, well, I'll be focusing actually, I shouldn't just say Big O notation. I should be talking about logarithms. Today we're going to be talking about logarithms. So we actually have done a couple of examples that use logarithms already, but this next session will be specifically targeting logarithms. So if you're wondering, oh, Dan, what we can do with logarithms today, we're going to see how logarithmic functions behave when it comes to things like when you have exponents inside of them, how and so-called logarithmic bases, how do they change when it comes to Big O? We talk about all these juicy bits here. So I thought before I get into things here, I'm just going to leave this chat open and everything. The TTS is on. So if you're watching this on Twitch, for example, you're welcome to type there and it'll pop up right here audibly on the chat. On the stream itself, but also keep in mind that if you find yourself wondering, because this came up last time, it's like, okay, so like they weren't hearing the TTS when I was doing the examples. It's because I usually turn it off. So when you don't see visibly the chat, that means the TTS is on. I can hear it. It's just that you won't be able to see, like audibly hear the TTS on your end. So I'll still hear it. So sometimes people leave funny jokes in there about what we're doing right now, and sometimes I'm laughing at something, but you aren't seeing it on the stream itself. It's just in the chat. This is something that you'll get to take a peek at maybe after the example or be here live. It's a good time. It's a good time. So anyways, let me cut to the chase. So other than that, I hope you're having a wonderful day. So let's get in on this. So before I get to our session per se, I'm going to start just with the definition of Big O. So a formal definition of Big O. This is how we're typically using it in Big O Bootcamp. I haven't put the hat on quite yet. I have to put the hat on when we get started. So I'm just doing this more as a preamble. So just as a quick reminder, let's talk about what Big O is. So Big O notation. So suppose I give you two complexity functions. So you might ask, Dan, what's a complexity function? So first, just to give you an idea what a function is. Now keep in mind there is a more formal definition, but I usually like to use this intuition with people when they're not really thinking about things that deeply, is that if you have a function, suppose it's called f. I'm going to describe it more like it's some machine, which is it's a useful conception of what a function is, at least in computer science. Is you can imagine this takes an input, it may take in multiple inputs, and it produces output. So if I give you, say, input called n, and we give it to f is the name of the function. Very often you'll see me write, for example, you'll see in a moment, let me see. So, but as output it produces f of n, so that's how I would say this. Likewise, sometimes just as an abusive notation, I will also write f like this, just to show you the parameters of the function. But I must stress that most of the techniques I'm showing you here don't necessarily rely on there only being one input. It's just that it's convenient for our discussions here because most people are familiar with just functions with one input. So this would be the input here. It gets fed to the function. The function is called f, that's its name, and it produces output we call f of n. So if the function is called f, its output is f of n. Likewise, if it was called g, you'd call it g of n for the output, and I would write it maybe g with the parentheses after that with an n. Now, a complexity function, just for the sake of clarity, is it takes in a positive integer, and sometimes for convenience, sometimes we have it where it's a non-negative integer, but for us here today, specifically because we're dealing with logarithms, we will always presume for this discussion that it's going to be a positive integer, as per what I initially said. It puts it in a positive integer and spits out a non-negative real number. So it could be 0, it could be 1, it could be 2, it could be like 10,000, it could be pi, it could be 1/2, it could be square root of 2. Notice that it's not negative, which doesn't make a whole lot of sense in the context of how we use big O notation in computer science. Now I must stress that, remember, big O notation is a mathematical concept. It's not just strictly tied to algorithms. So the kind of things that we do here may not necessarily need to reflect themselves in every single mathematical setting. And sometimes the intuition behind the big O notation and how we use it can be a little different than the more slipperier notion of what the big O can actually be capable of expressing. So we've actually talked about some of these things in the past. So suppose I give you two complexity functions f and g. We'll say that f is big O of g, which I'll very often in this session write with a set theoretic in, so that you would read that as is in or is. But also the other convention that gets used very often is an equal sign. But I must stress that this equal sign is not actually saying equals. I've talked about this before. So whenever you see me say f is big O of g, you can write this set theoretic in, or you can write this equal sign here. But I must stress it's not actually saying equals. It says is. So I would read this as f is big O of g, regardless of these three symbols. Sometimes you could say is in as well, which has its own interpretation as well. So we would say this is the case if and only if. Now, in logic, what this means is that if this is in fact the case, that if f is big O of g, it has to be whatever comes after this also has to be true. If that is false, then whatever comes after this has to be false. It's a logical equivalency, okay? So I'm saying if this is the case, then whatever follows after this also has to be true. If this is false, then most certainly whatever is after this has to be false. So anyways, if and only if there exists, there exists two constants. A positive real constant. So this blackboard R means real set of all real numbers, where the plus adds and says positive real numbers. So this is we're not talking about 0, we're not talking about negative numbers, we're talking about anything that's bigger than 0 when it comes to real numbers. And there's another constant called n0. Now keep in mind, these are just names. Sometimes in our proofs we'll want to give these different names if we're talking about something specifically, but these are pretty common names to give these constants. But they don't have to be these ones. They're just names. Just like this function is a name, f here. So n0, such that So note that it's a positive integer. It can't be 0. It has to be 1 or greater. Such that for all n greater or equal to n0, it has to be that f of n, so the output of this function, f has to be less than or equal to c times g of n. So this has to be true for all n greater or equal to n0. So the game in town is you have to find these two constants. But the thing is, when you pick these two constants, it has to be that this inequality is true, but not just any one specific value. It has to be true for all values of n greater or equal to the second constant. So the intuition behind this that you can imagine is that you plot these out on two charts, and you can say, hey, look, one of these functions, it dominates the other one, so it appears above the other function when you plot them out at some point and after that. So the idea is very simple. There's a sufficiently large value of n, where every value after this one, so we'd call this n0, and keep in mind it could be that value or greater. It doesn't have to necessarily be the smallest possible value, such that f of n is bounded by a multiplicative constant, it's a constant multiple of g of n. So, just as a quick example of how you might use this, you might write n is big O of n. In fact, we proved this last time. We proved that this is the case. In this case, what you would do is you could just pick c as 1 and n0 being 1. And of course, you would have to still lay out a proof for this. Now, in this case, since you know about big O being reflexive, you can just say, due to big O, the big O notation being reflexive, or the reflexive big O satisfies the reflexive property, you can get this. But you just use the same proof that I gave you previously. Likewise, you could say other things, such as n is big O of n squared. So in this case, the way this works, notice that the intuition behind this is that it's an asymptotic upper bound. So notice that it's bounding in this direction. The g part always goes above it or it's equal to it. So it's an asymptotic upper bound. So the asymptotic part about this is that there's a sufficiently large point such that everywhere after that it has to be that this is true. So keep in mind that n0 doesn't have to be just like some small number. It could be actually fairly large. As we've seen actually in an example the other day, I gave actually a constant which was rather big. It was actually rather big. So let me just, so actually in that case, I'll let you think about what constants you would pick. I would tell you it's pretty close to the ones that you'd pick here. They would work perfectly fine. But I must stress there's a couple hard and fast rules, but we talked actually a little bit about some of these things before. Is that, say for example, instead of it being n, say it's 1000 n. You can show that 1000 n is big O of n, for example. Multiplicative constants like these, the rule is that these get dropped. Likewise, additive constants, like if I added, I don't know, 10 to the power of 6 to this, those get dropped too. So we care about really just what's happening. Like you'll notice that this tells you very quickly how the function will scale. That's the intuition behind it among one of several. In the way we talk about in computer science, you can think of it as scale. Like if you think of this function as a complexity function that measures the time or the space being used, what this represents would be the number of operations, or it could represent a rough approximation of how long it might take if you have the appropriate measurements in place. That's kind of important to do this. I always get annoyed by exercises that say, oh, you have, suppose you're given this, and you have, the algorithm runs for like 10 seconds, how long should it take? Without knowing how long one operation of this takes. So they aren't even giving you any rough approximation of how long an operation should take. I always get annoyed by those kind of problems. So, because it's a misunderstanding of how big O works. So anyways, Let's talk a little bit about a couple other things here. So we talked about the multiplicative parts. So that's the intuition behind it. But remember, this is just intuition. You have to convince yourself that these are actually true. So that's the point of Big O Bootcamp. Is I give you complexity functions like these, which might represent the number of operations of an algorithm in the worst case, for example. And I want to know what its Big O is. So right now we're looking at a variety of different ways I can kind of get nice simple rules for doing this and how you can formally derive all of these rules. So we've talked actually about plenty of them up to this point. But most certainly we haven't talked about all of them, and there's a lot of them, and I most certainly won't say, okay, even all of them isn't necessarily going to be cutting it for us, because this topic easily overlaps with just doing general analysis. Because remember, this is just a formal definition, and these are functions. So functional analysis, or any kind of analysis of the kind that involves functions of this kind, can easily extend into all sorts of other domains. So I must stress that I'll be mostly focusing on techniques that are going to be mainly aimed at computer science audience. So things that usually the complexity functions will look like. They won't be strange, obscure things for a computer scientist. They will be something much more appropriate for, or say, a computer science student, or somebody who's interested in computer science, or anybody. These certainly won't be strange things that don't even like you would never imagine them. But I must stress that that those types of things also matter too. So just take it in mind when I say all. I'm not actually talking about like every possible enumerated way you can handle a complexity function, but this is going to be, I would rather consider it kind of a basic comprehensive way of going about it. So anyways, I guess with that out of the way, and we don't have any questions, it's rather quiet here today. I'm just going to take a quick peek just to make sure nothing's going on over here. Let's see here. Just got to always take a little peek about this stuff. I'm just trying to think here. There might be... Taking a quick peek before I get too much into this. Okay. Yeah, I think we're doing okay. Just keep in mind that even though it may not be very busy right now, I know that there's people that do check out these things afterwards because they can't come to the live stream. So, like I said, these things are often useful. They're very helpful resources. Like I say, I'm giving you all the tips and tricks that I can give you to essentially ace any one of these types of exercises. Speaking as somebody that's been a computer science professor and has taught courses like these for a number of years, is that a lot of professors sort of use a lot of these common techniques, or even your blissful ignorance of them, because often they don't have the time to talk about all these techniques, or some just don't know them themselves. It's just unfortunate. And that's okay too, as long as they aren't teaching you. So that's usually not a wise thing, to be teaching things you have no idea what you're talking about with. But anyways, what I'm going to do now is I'm going to erase the board, then we're going to get started, okay? So we know what the Big O definition is. We know the fundamentals when it comes to how you might use it. But remember, the goal here is to study, given complexity function, I want to know what its Big O is. And I'm trying to give you a variety of tools and tricks that you can use, and how the formal underpinning of them. So like, why are they true? So we're going to see some examples for a variety of different things you might encounter. But I'm going to start off by doing a bit of a review. So let me just get my hat on, because we're going to be getting started here. And cross my fingers I don't knock anything over. And let's get on this, okay? So let's get on this. And remember, as usual, if you have any questions, just put it in the chat. I'm very happy to answer any of your questions. But keep in mind that if it's something a little bit more delicate to deal with, and it's not something I can easily just talk about at the moment, I'll usually reserve it till after I finish the example. But if it's something simple for me to address, I'll happily address it when I can. So, anyways, So today we're going to be having fun with logarithms. So before I can do anything, I need to talk a little bit about properties of things such we call exponents and their connection with logarithms. And we'll talk about a couple properties that logarithms have. And also, and keep in mind, this is by no means a complete or exhaustive list of properties, but most certainly some of them will be useful if you were trying to study these types of things. So I'll lovingly call this session Fun with Logarithms. I hope you're having a wonderful day. And I'm going to put a smiley face on that. Very happy. Very happy. Don't forget to smile. It's always something important to do. It's a good workout. So anyways, before we really talk about logarithms, I'm going to talk a bit about exponents. So I'm going to try to go a little bit faster over this because I typically expect this to be more grade school education. Like we're talking about like high school. So I would hope that you have some understanding of some of these things, but at the same time, it's okay. I'm going to do a bit of a review. So recall, for any real number, x that's not equal to 0, and what we call the exponent or power, and exponent or power n, which is going to be a real number, rewrite x to the power of n, where we call x the base of the exponent. So these two are rather important for me to bring up, just for the sake of discussion here, is that we're going to use this terminology of a base and an exponent very often. So often you'll read this as x raised to the power or exponent of n, or you'd say x to the power of n. So you might ask, Dan, what does this mean? Well, I'll just give you an intuition when it comes to just integers, because this will work well enough for our discussions here. If exponent n is an integer, then what x to the power of n means is it's x times x times x times all the way where we have n of these. So we have a product of n x's. Note that if you're wondering, as an aside, these are a couple things to keep in mind, is that x to the power of 0 is equal to 1, and x to the minus n is equal to 1 over x to the power of n. So now there's a variety of different properties that exponents have, and you're going to see that these are going to translate very naturally to logarithms. So just for the sake of consistency, I'm just going to let real numbers x and y not equal 0, and m and n be real numbers. So these are some short properties. So this is going to be a list of properties that exponents have. So some of these I may have mentioned in the past, but here's first property is the product property. So the product property works like this. So if you have a product where the two terms you are multiplying have the same base, you can add them. So x to the m, x to the n is no different than me writing x to the m plus n. Just as an example, 2 squared plus 2 to the power of 1 is equal to 2 to the power of 2 plus 1, which is equal to 2 cubed, which is equal to 8. That's a very liberal use of equal signs, okay? So you can check this very quickly by noticing, you can check this computation. Notice that 2 squared is 4, and 2 to the 1 is just 2, so it's 4 times 2, which is just equal to 8. But also you can use it in a different way too. So for example, if I have a larger exponent, I can also decompose the number into multiple terms using this property. So this is another thing to keep in mind about this. So it doesn't just go like one direction. You can unwind this. So if I know 2 cubed, well, 2 cubed is the same as writing 2 to the power of 2 plus 1. So I can do the same thing here. So for example, if I have 2 to the power of 8, if I want to do a simpler calculation here of what 2 to the power of 8 is, I can go 2 to the power of 4 plus 4, because that sums up to 8. But what is this? Well, it says that I can express a sum like this as a product of two of the same base with those exponents, right? So that's 2 to the power of 4 times 2 to the power of 4. But 2 to the power of 4 is just 16, so this is 16 times 16, which if you know your powers of 2, this would be 256. But that's okay. So that's just that's just how you can use this product property. So I'm not going to prove this property here. I'll give you an example of a proof for one of these properties as we come up. So the big thing that I really want you to notice here is that if you have 2 of the same base, you add the exponents. So just take note of the fact that you're adding the exponents. This is important. So just take note of that. Now, the next thing I'm going to talk about is the quotient property. You're going to see that this is going to be like, because it's natural, because if you were doing the reverse operation of multiplication is division, because you can express division in terms of multiplication. But I'm not going to go too much into detail about that here. It's a whole other fun discussion. Like you just look at product, like if I have x to the m and x to the n, it's no different than me writing x to the m over x, sort of multiplying it by, so I have x to the m times 1 over x to the n, for example. Notice that this would just be like if I divided x to the m divided by x to the n. So this is what I mean. So this shouldn't surprise you that if you know that 1 over a something, if it's x to the n, for example, you know that's x to the power of minus n, right? So it shouldn't be very surprising that instead of adding, you end up subtracting. You get a difference. So we have the quotient property. So it's x to the m over x to the n. Well, this is x to the m minus n. Just as a quick example. Like I said, a lot of this stuff's pretty basic, but it's clever and nice. So if I have 2 to the power of 8 divided by 2 to the power of 5, this means it's 2 to the power of 8 minus 5, which is equal to 2 cubed, which is equal to 8. I encourage you to double check that calculation. So, next, let's talk about the power property. So this is number 2. Let's go number 3. The power property. So if you have something being exponentiated like this, x to the m, and you have outside of here, it's getting exponentiated again through what is a product of exponents like this, naturally you'd see that it's actually going to be expressed as a product, not a sum. So if you have this, x to the m, and you raise this to n, it should be x to the m times n. And if you're thinking about this in terms of integers, this shouldn't be very surprising to you. If you actually think about this carefully, notice that if you just put any other number here where x to the m is, like say that's a. Well, you would say that that is just a to the n. And you know, if we think of the exponent as an integer, so just this intuition is very natural if you're thinking about an integer, although this property is much more general than this. You can imagine it's a written out n times, right? a product of a n times. Well, if each one of them is x to the m, instead of just being written as a, well, you have x to the m written out n times, right? So you can use, in that case, if we're talking about this, we can use the product property. And you'll notice that all I'm doing is I'm just summing up I'm taking x to the m and I'm doing this n times. So I'm summing up m n times, which is m times n. That's pretty cute, right? So just as a quick example, 2 cubed raised to the power of 4 is 2 to the power of 3 times 4, which is 2 to the power of 12, which if you're curious about what that is, that's 4,096. Double check that calculation. Now, another one that has come up before, or at least is something that you could discuss, is power of a product property. So this is the one that we are using. We actually use this for when we talk about properties of big O. I use this property explicitly. So if I have x times y raised to the m, this is no different than writing x to the power of m times y to the power of m. So notice the parentheses. It's x times y raised to the power of m. Now you might ask, Dan, how is that the case? Well, let's think about it. You have x times y times x times y times x times y times x times y. And if m is an integer, you will see quite clearly that this is written out m times, right? Well, all you do is, because multiplication is commutative, I could just simply arrange all of the x's together and all the y's together, and then I can just group them like that. And then I have m many x's and m many y's. And you'd use this product property I have over here on the left board, and you just sum them up, right? You can just view it that way. That's one way you could go about this. There's several other ways you can. But that's one natural way you can look at this if m is an integer. So just as a quick example of what I mean by this, if I have 2 times 3 squared, what I'm saying is it's 2 cubed times 2 squared times 3 squared, I wrote down cubes, is 4 times 9, which is equal to 36. And like I said, you can always expand the terms here to see what I mean. So if it's 2 times 3 squared, well, that's 2 times 3 times 2 times 3. Well, this is the same as me writing 2 times 3 times 2 times 3 like this. Then on top of that, you could just simply rearrange this so all the 2's are together and then all the 3's are together. So 2 times 2, 3 times 3. But this is just 2 squared times 3 squared. Boom. Is that nice? Okay. Now, one thing I also want to bring up, just as a remark, and I'll have more discussion about this in the notes, is that very often, when we do we perform algebraic operations. So for example, you know when sometimes you add numbers to both sides of an equation, or you take a difference on both sides of the equation, or you divide by both sides, or you take logarithms of both sides, which will be relevant here. You might ask, Dan, what does that even mean? So like, what does it mean for taking logarithms to both sides? Well, here's the first thing I really want you to think about, is that if we have it where 2 elements are equal to one another, well, if I apply them to some function, then it has to be, because, just remember we talked about our machine we had earlier? So we imagine the function as a machine. So if I give you the input and I spits out output, right? If I give you the same input, it should output the same number, right? So if I have 2 elements that are the same, they're equal to each other, then the machine, the function, should output the same result, right? So naturally, if I have 2 things that are equal to each other, if I apply an operation such as a logarithm to both of the sides of the equation, which has both the same elements on both sides, they're equal to each other, then it should be that the result of this should be, if I apply logarithms, so if I put I put those 2 elements as input to the logarithmic function, then they should have the same value. That's because if I have two elements A and B, if they're equal to each other, then log base B of A, I shouldn't give a base yet. Log A is equal to log B, and I haven't defined what a logarithm is quite to this stage, although I have done so in previous sessions, which is why I'm saying this. And this is true in general settings, so this is because a function is what we call well-defined. So I have some more discussion about this in the notes. I just thought it would be an interesting thing to discuss here. So you might say, Dan, these are rather interesting things to know about exponents. Well, let's start talking about what a logarithm is, seeing as I started talking about those. So let's start talking about that. Now, I gave you a list of properties. Now, there's actually a complementary list of properties that logarithms have that it shouldn't surprise you. I know I'm saying that a lot today because I think that a lot of this is review, but it doesn't necessarily have to be. This may be your first time being exposed to this. That's okay too. Everybody is welcome. If you have any questions, just let me know. So let there be positive reals. So these are going to be positive real numbers. X, Y, and B, where B is not equal to 1. See why in a moment why it may not make a whole lot of sense for B to be equal to 1. Then there are the following properties for a logarithm. Following properties for logarithms. Now, just as a quick reminder, what a logarithm is that when we exponentiate, we have a base of the exponent raised to some power, and we get a result. That's the result of exponentiation. So I'm going to ask the inverted question. So imagine I give you, let's go b to the, suppose I give you let's go b to the, I don't want to use x over here because we're going to use x and y in specific ways. But I'll just use, let's go b to the d is equal to x. Now, in exponentiation, what you do is you take b and you raise it to the power of d, and you get, as a result of the exponentiation, x. Now, what I would like to know is if I give you the base, b, and I give you x, what is d? I want to know what that is. That's what the logarithmic function is. That's what logarithms are. So the way I would re-express this in terms of a logarithm is I would write log base b of x is equal to d. So that's the definition of a logarithm in about a minute. So let's talk about some properties now. So you can see that there's a close relationship logarithms have with exponentiation. Just the question now is, instead of it being what's the result of raising b to the exponent d, I want to know what d is. So here's some properties, and you're going to see that they're going to be somewhat related to the things we just talked about. So a product rule. So this is going to be the product rule of logarithms. So I'm just going to call it the product rule just for the sake of brevity here. But I mean the product rule of logarithms, or product law of logarithms. This is log base b of x times y is equal to log base b of x plus log base b of y. Now, if you think about this very carefully, if you look at this statement, you notice I have log base b of x is equal to d. So this is the result. This is like the expected, sorry, I'm getting very excited here. The expected result of log base b of x. So what does this mean? This means b to the something is equal to x. Well, if I give you that b to the something is equal to x times y, well, let's think about it. I have b to the something is equal to x times y. Well, we have actually looked at something like this before. It should remind you of the product rule, the product property of exponents. So if I have some number, and this is the result of the exponentiation, well, what does it mean? B to the something is equal to x times y. Well, think about this carefully. It would be b to the something is equal to x. So that would be whatever x is. And then you have b to the something is equal to y, right? But well, that's the product, right? Like, I'm just trying to give you an intuition behind these, because I'm not going to prove all of these for you up here, because like I said, most of this I consider review for the discussion that we're having. But I'm trying to give you some intuition behind this. So the point here is that if you have a product like this, we know that if we have a product and we're trying to express it in terms of exponentiation, we already know that when you have two of the same base, notice that these are the same bases. So this is the same base here. So it's b to the something is equal to x times y, right? So what I'm saying is, if they're the same base, you know that if you multiply, you should expect that their exponents sum to each other. It's a sum, as you see right here. So if you're not sure about this, just look at this definition carefully and try to put this in place for the rule I have here. So that's the first one. Naturally, if I give you the quotient rule for a logarithm, well, you should expect that log base b of x over y, so x divided by y, it should be a difference, right? Just like how we took the exponents and we had a difference as opposed to an addition. So that's the quotient property or quotient law of logarithms or quotient rule of logarithms. Another one that's helpful to be aware of is the power rule of logarithms. Many properties can be derived from this one specifically, but these two are also very helpful. The power rule of logarithms. So this is where if I have log base b of x to the y, so notice that this is all together. It's x to the power of y. Well, if you look at this, it's x happening. It's like x, whatever the result of this is, but it's done y times, right? So you would have y times log base b of x. So I thought, before I get too ahead of myself, I'm actually going to prove this property here for you. So if you're wondering offhand, Dan, where did this come from? Let's do the proof here. So I'm going to we're going to prove number 3. And to do this, I'm going to use the definition of a logarithm. So let z equal log base b of x. And I'm going to use the variables as I've defined them up here. So note that the theorem statement is going to be more precisely stated in the notes, but the variables should be the same ones I have up here. So let z be log base b of x. So if you think about this carefully, what I've just written here is actually just not that much different from what I wrote right over here, right? So I'm just going to write out the definition of a logarithm. So by the definition of a logarithm, it must be that b to the z is equal to x, right? That's what this says, right? If I log base b of x is equal to d, then it has to be that b to the d is equal to x. So if z is equal to log base b of x, then it has to be b to the z is equal to x. Because that's the same base, right? So we have this. Now, I'm going to use a property that we had from exponents. So watch this. Then we're going to do what I just described a moment ago. This is actually why I brought this up, is that because I know that this is in fact an equation, these two sides are equal to each other. So what I'm going to do is I'm going to raise both sides of this by an exponent. Then, this then looks a little sad. Then raise both sides of the equation by exponent y. So I'm going to kind of cook up what this is for the matter of the statement. So I'm going to try to derive this statement using this much more basic definition. So here we go. So I'm going to raise both sides. So that means that x to the y has to be equal to b to the power of z raised to the power of y. But what is this? Well, because of the properties we talked about with the exponents, it's b to the z times y, right? But I'll write it as yz because the order shouldn't matter. Yz. So that means that log base b of x to the power of y is equal to log base b of b to the y times z, right? That's what it means. That's a consequence of this. Because x to the y is equal to b to the yz. So if I look at it in terms of logarithms, they should be equal. So now here we go. Now I have this. Well, log base b of b to the yz is equal to yz, right? That's what the answer is, right? Because so it's asking b to the what is equal to b to the power of yz. Well, this tells you the answer, right? It tells you it's yz. It's sitting right there inside those parentheses there. And what's yz? And yz is equal to y log base b of x, right? So y times log base b of x. Hence, well, has to be then that log base b of x to the power of y is equal to y times log base b of x. And we're done. So just to kind of recap this, we figured out that that x to the power of y, so specifically log base b of x to the power of y is equal to log base b of b to the yz. Well, when we see that, the right-hand side over there is just equal to yz, right? But we established that yz is just y times log base b of x because of the first way we defined what z is. And then lastly, since we knew that those two are equal, this has to be the case too. So for those that are just looking for a very simple way to look at this, which is effective enough, it's easy enough to remember, is you can imagine it like I'm dragging the y out front, or I can even put it back in. So I can take this exponent, I can drag it out in front, or if I wanted to, I can put this back inside of here and exponentiate everything inside of the parentheses here for the logarithmic function. That's a very simple way you can use the power rule. So, I'm just trying to think of anything else that I need to cover here. 24. No, that's everything for this. So are there any questions or anything? I'm just going to put the chat back up. No, we don't have any questions. It's rather quiet here today. But yeah, we've seen a lot of these fundamental properties. There's other ones too. We're going to see at least one more pop up. But we're going to start doing some examples where we're actually proving big O claims next. So let me see here. We're done with that. We're done with this. Those can go over there. Yeah, we're getting some really juicy stuff coming up. You're going to see how we're going to generalize a lot of the things we've talked about up to here. So do you see how there's a bridge between logarithms and exponents? Is that there's a very natural bridge between the two. So for example, we've seen how when we had a product with the same bases, we noticed that if we have a product of two, like x to the n, x to the m, it sums them, which naturally gets translated as a sum over the logarithmic function like this. Because remember, this tells you the answer to those, right? It tells you, okay, what did I need to raise the exponent to? But this is what the exponents are, right? It's very natural. It's also a rather effective way if you ever find yourself trying to work arithmetically with large numbers. Very often logarithms can be used for simplifying those calculations, because now you're dealing with just additions and differences as opposed to products and divisions. Is that you can just play around with these exponents using sums, which is much simpler to play around with. But in algorithms, very often we run into the logarithmic function when we are analyzing algorithms that use a so-called divide and conquer approach. So for example, and it doesn't have to, but it most certainly is, it's one of the ways this can happen, is very much where you have it where you have the opposite effect of exponentiation. So I thought I would just make a side remark before we move on to our next stuff, because sometimes people ask me, Dan, why should I care about what a logarithmic function, why should I care what a log is? Like, what is log? Like when I run into log, like big O of log n, in time complexity analysis, like I run into an algorithm like binary search that runs in big O of log n. You might ask, Dan, where does this come from? Like, what's the intuition for, what's one intuition that you can have when we talk about logarithms? Like what? And I've been trying to be rather reserved at the way I've used this, but I'm hoping right now I can do this. So when we talk about exponentiation, so for example, if I give you something like 2 to the power of n, well, if I think about this in terms of increasing values of n, so 2 to the power of 0 is equal to 1, right? Well, 2 to the power of 1 is just 2, right? 2 squared is 4. 2 cubed is 8. So notice every single time it's doubling, which shouldn't be very surprising every time you multiply by 2, right? It's growing exponentially. Well, you might say, Dan, like how do I know, like if I have this exponentiation happening, like every time it doubles, because it's 2 to the power of n, I would like to know how many times that's happening. So for example, if I have this right here, and you might say, Dan, how many times does, say, if every time you do this multiplying by 2, how many times is that happening? Well, notice that this happens once, twice, 3 times. And that shouldn't be very surprising, right? Because every time you're multiplying by 2, every time it takes whatever the result would be, multiplies it by 2. So it grows exponentially like this. And a lot of things in nature do grow exponentially. Things like if you look at things like virus growth, things like that. A lot of things at that level tend to grow exponentially. Not all of them, but many, well, I would say many of them do. So the point is that if you look at this carefully, 2 to the power of n right here, you can phrase this in terms of my question I had earlier, right? Well, we had b to the d is equal to x. So suppose I had this. 2 to the n is equal to x. Well, if you rewrite this, it's just log base 2 of x is equal, log is equal to n, right? So notice it's literally the inverse of this exponentiation, this growth exponential. So if you're thinking about what a logarithm is instead of it be asking the question of how many times, so if every time I take this, I'm multiplying by power of 2. So I have 2 times 2 times 2 times 2. I want to know how many times that happens, which is the inverted question. It's an inverse of it. So if I want to know, say if I wanted to know how many of these dots there are at a given level, that tells me the result of 2 to the power of n at that given level. If you think of this like a tree, for example. The inverted question is how many multiplications had to have happened to get to that level in the first place. So if you're looking at this as a natural question, and it's very intuitive if you actually think about it in terms of if I have an overall result, how many times, how much work gets done, so how many times am I cleaving that work down, to break it into a smaller problem. That's the natural way you can interpret this. So, for example, with binary search, imagine you have an array of length n. Suppose that, every time you have a search happen, you can either take on the left side or the right side. What this is doing is, instead of exploring everything, what happens is you just simply discard an exponentially many elements that you may consider, if I have 8 of them. And then naturally you would consider going down every time. And every time you make a search, you discard half of this tree every single time. And this naturally corresponds to this, right? It's the same question. And that's one way you could see how a logarithm may manifest itself. It manifests in many different ways, but most certainly this is one way you can have it happen. So sometimes people ask me this question. That's sort of a side remark. So what I'm going to do next is I'm going to erase the board. And we're going to get to our first set of proper big O examples. So now I've just done my review of logarithms. So I encourage you to try using them actually on the examples I gave you earlier. So I want you to try plugging in the numbers from earlier on and see if they match up with what you would expect to happen. So just remember the relationship a logarithm has with exponentiation. That's the big thing. I'm just going to erase the board over there. So let's... Okay. So we're going to start off with some simpler examples, and I'm hoping that these examples illustrate the important difference between a constant and something that relates to the input of the function itself. So I'm hoping that this clarifies this kind of natural question of what happens when you have some exponentiation happening within the logarithmic function. And we ask the question of, okay, if it's a constant for the exponent versus not being a constant for the exponent, what happens? So we're going to talk about that right now. So the first example we're going to look at is as follows. So this is technically a general claim. So we're going to assume positive real numbers. Positive reals B, K, where b is not equal to 1. Now, while I'm at it, seeing as I should address this at some point, why doesn't it make sense for the base to be 1? Well, let's think about it. At least if we're thinking about this a little bit more generally. So what it would mean is that if we put on our definition of a logarithm, what we would say is base of the thing. So if I have log base 1 of x is equal to a something, say y, what this is saying is 1 to the y is equal to x. Right? Now this is not terribly interesting if you actually look at this, because it's 1 to the something is equal to x. Well, notice very quickly that this actually, is this like something that has, like if I say put in x, it's going to give me an answer, right? So if I ask what x is, there's only really one answer, right? There's only one answer to this always. So notice that if you try to put in like 2 here, like say if this is 2, can you answer that question? So I want to know that 1 to the something is equal to 2. Is that going to work? No, right? Because 1 to the something is always equal to 1, right? So that's why b can't be equal to 1. It has a lot to do with the nature of the fact that exponentiation And logarithms, they're inverses of each other. So if you actually look at the question and ask the question backwards, is there a unique y such that log base b of x, it becomes much harder to do, to have a unique value for that. So if I have this, where b is not equal to 1, then this is the following. Then log base b of n to the power of k is big O of log base b of n. That's the first thing we're going to try proving. Now, the first thing I really want you to look at is that notice that the function is defined in terms of, it's like log base b of n, right? But also notice that this is just some constant. It has nothing to do with the input over there. It's for positive reals b and k, which you could presume here are constants. They're fixed. So now the first thing we would like to do is get an idea of, okay, well, what happens here? So let's see. We'll see what properties of logarithms we can use to prove these claims. So as per usual, we should lay out the game plan for what we need to accomplish. So we find some c, which is a positive real number, right? We have to find the two constants. And n0, which is a positive integer, such that log base b of n to the power of k is less than or equal to c times log base b of n. And this has to be true for all n greater or equal to n0. So remember, that's the game plan. Usually it's quite a good idea to get cozy with this definition. So I'm just going to switch markers. So you might be staring at this and say, Dan, well, if b and k are constants, they're fixed. So what can I do? Well, think about it. We had a property we called the power law or power rule of logarithms. And it told us that we can pull this exponent here, k, out front in front of here. Now notice that if k is a constant, then there's a very straightforward way of handling this. Does everybody see it? So if I pick c first, let's think about this. Sorry, we had a little bit of a blip with the video there for a moment. let me just check on that. So I want to make sure we're doing okay. Okay, I think we're doing okay. There's a little bit of a blip there. So anyways, the game plan here is we need to figure out how to make that inequality work for all n greater or equal to n0. And the natural intuition here, sorry, I'm getting very excited here. The natural intuition here is that you know k is a constant. And secondly, we know the power rule or power law of logarithms, which says we can pull this k, put it out front in front of here, so you get k times log base b of n. But if you look at that very quickly, you see that if I make c equal to k, we're done, right? I just need to use those properties. So pick c is equal to k, because I'm just going to play my lookalike game. So I'm just going to apply our lookalike approach to just make this work. But I have to do a little bit of massaging to the left-hand side to make that possible. So I'm going to pick c is equal to k. Then we find n0. We find n0 such that for all n greater or equal to n0, log base b of n to the power of k is less than or equal to k times log base b of n. Now I'm just going to use the power rule or power law, power rule of logarithms. We can say the following: that log base b of n to the power of k is equal to k times log base b of n for all n greater or equal to 1, right? So we're going to just choose n0 is equal to 1, and we're we're done. So therefore, now you might ask, Dan, where was the step that you got from the right-hand side? Well, notice that I'm just applying the power rule of logarithms, and it's right there. So which, if you find yourself wanting to advise your reader that this is the right-hand side, you can always say, which is the right-hand side, somewhere in here. Therefore, by the definition of big O, because remember, we have our two constants, we need to use the definition of big O at this stage to finish off the claim. Big O, log base b of n to the power of k is big O of log base b of n. Now, you'll notice that for some of you, you might say, Dan, why are you writing that base every time? I'll get to that in a bit. So that'll be something I'll talk about eventually. So this tells you right away that if you have a constant in the exponent like this, so when you have an exponential where this is a constant, or at least it's independent of the input, what it tells you is that this can go away. It doesn't matter. So there's a couple of ways you can imagine or think about this. Is one, through the way we talked about here in the proof. Another way you can look at this is if that's a constant, this is no different than me writing n times that, and it's some constant, right? So really it's just a finite number, but it's a fixed finite number. Where it's going to be that I'm taking n times n times n times n, doing it k times, and inside of there I can apply the product property if I wanted to, which is another way to derive the same outcome here. So notice it's a constant number though. So a very natural question is, okay, well, what happens when you change this up a little bit? So I'm going to do something a little bit spicier than just that. So let's see what happens. So in particular, what happens, actually, before I even get to that, I'm going to push this principle even further. Just because I really want to convince you that a constant like this doesn't make much of a difference in terms of big O. So I'm going to push it even further. So let's consider what happens if I take a sum of logarithmic terms, each with their own exponent, and see what happens. Now keep in mind, this is just one way to manifest this. So the claim I'm going to prove here for you is that the sum from I is equal to 1 to k of log base b of n to the power of I is big O of log base b of n. So let's play around with this. So it's going to have a very similar feel to what I did earlier. So let's see what happens when now I deal with a sum like this. So now I've raised the stakes. So now each one of these is some number that goes from 1 up to k. So it's log base b of n to the power of 1 plus log base b of n to the power of 2, and so on all the way up to log base b of n to the power of k. So now I have multiple terms I've introduced, more than that were over there. So I'm going to push this even further. So let us find constants. Remember, we always have to write out our game plan. It helps the reader. You'll notice that I'm formulating it in the way the definition would work. If I do this, then I can just invoke the definition, then we're done. And n0, which is a positive integer, so that the sum from I is equal to 1 to k of log base b of n to the power of I is less than or equal to c times log base b of n. And this has to be for all n greater or equal to n0. That's important detail. It's a very important detail. Don't miss that. So, last time we seen that we can make the constant equal to k and then we'd be done, right? But based on what you see here and how we understand what this sum is, notice that we can't just pick c is equal to k, because now we have more terms over here. But we can use the same idea, right? We can push that, we can use that power rule again, but we can push it a little further now. So notice that each one of these exponents is a 1, then a 2, then a 3, then a 4, then a 5, then it goes all the way up to k. So here's my suggestion is we pick, because I want to play lookalike the same way I did in previous lessons. So pick c is equal to 1 plus 2 plus 3 plus all the way up to k. Now if you look at this carefully, I've actually just written out an arithmetic sum. So this is just sum is equal to 1 to k of I. Now you might ask, Dan, what are we going to do with that? So what are we going to do with that? So we want to know what that means. So let's think about this. Now this is one way you can derive this if you need to offhand come up with it. Here's a geometric way you can interpret this. But I must stress that there's multiple proofs for this. By the way, this picture is not a proof. Just to be clear, you have to formalize it more. So if I have 1 plus 2 plus 3, I have 4 of them. And suppose I have this go up to k. So that means that there's k many of these columns, right? So it's k of them. Because I go 1 plus 2 plus 3. I want to know how many boxes there are here. If I know the answer to that, then I know what that sum actually equals. Well, here's another fun little trick that you can do. Well, you could take this and imagine you take this listing of boxes that I have and I mirror it. So I take this and I imagine I flip it over this diagonal here and I put the same thing that I have here on the opposing side. So for example, what I mean by this is that wherever I have the k here, I'm going to put one box here, then you would have 2 boxes here, 3 boxes, 4 boxes, 5 boxes, all the way up to the last one having k boxes. And now, if you remember back to your lessons on how to compute the area of a rectangle, well, notice this dimension is k. What's this dimension? Is that k? Or is it k plus 1? It's k plus 1. Well, what's the area of that? Well, it's k times k plus 1. But I want to half the area because the way I constructed this is I took the same number of boxes and I mirrored it over the diagonal. But I want to know what the area is. Well, it has to be exactly equal to half of this, right? Because I took it and I multiplied it by 2 by simply mirroring it like this. So this is actually how I can, this is one way I can derive this closed form geometrically, is I have k times k plus 1 divided by 2. So I compute the area of this rectangle and I divide it by 2. That's one way you can, if you ever find yourself forgetting about it, just draw some boxes like that. It's a piece of cake. So now this is my c. It's going to be k times k plus 1 over 2. Notice the way I formulated it, now it's in terms of k. And that is indeed still a constant because k is a constant. Don't let the fact that it looks a lot more sophisticated throw you off. It's not. Then we find n0 so that for all n greater or equal to n0, the sum, let me write it here. The sum from I is equal to 1 to k of log base b of n to the power of I is less than or equal to k times k plus 1 over 2 times log base b of n. Now, I'm just going to apply the power rule again, the power rule of logarithms. So notice the domain I'm using here for all n greater or equal to 1, because I want a statement that connects my selection of n0 to this next statement. For all n greater or equal to 1, observe by the power rule of, well, that's really funny. Oh, let me rewrite that. Of logarithms, we have the following. Well, what I could do is I can make use of summation properties in the following way. Notice that each one of these I can apply the power rule to it. So I can throw that I out front, and then we'll see what happens. Well, the sum from I is equal to 1 to k of log base b of n to the power of I. Well, each one of these, I just pull the I out front inside of each summand. So I have I times log base b of n. But notice that each one of these, I'm adding log base b of n every time. But notice that has nothing to do with I. So what I'm going to do is I'm going to pull that aside from this sum in a way that makes it clear to you what's happening. So the sum from I is equal to 1 to k of I times log base b of n. But what's this? We already established that's k times k plus 1 divided by 2 times log base b of n, which equals the right-hand side. That's the right-hand side. Which equals the right-hand side. So that means that we're going to choose n0 is equal to 1, because this statement is true for all n greater or equal to 1. And then now we could just use the definition of big O and we're done. Therefore, by the definition of big O, the claim is proven. The claim is proven. And that's the end of the proof. I forgot to put the proofs. That's one thing. I need to mark the end of the proof also in our previous example, because remember, that is a proof. These are both proofs. Normally I would write the phrase here, but I sort of ran out of space here. So just keep that in mind. But yeah, so now with these two examples, we can see that the exponent being a constant doesn't actually make much of a difference. In fact, you can take this even further and you could say, hey, okay, well, what if I made the I k everywhere? So then you would have just k plus k plus k plus k plus k instead of 1 plus 2 plus 3. You would have just k's. There's going to be exactly k many k's, right? So that's just k squared, right? So you'd see that you could just generalize this in many different ways. Now, let's revisit this example here, seeing as it's a generalization, or you can view it as a generalization. Actually, it's not really a generalization, it's more of an extension. It's an extension of the first example. We're going to talk about now how we can apply this when I change that k to be an n, and we'll see what happens. We'll see if this technique falls apart. So before I write out what we're actually going to prove, I thought it'd be a better idea that we kind of dive right into trying to apply these techniques. And then we'll see if it actually will be, what would be the outcome. So let's do another example. I must stress that this is still a claim, right? I'm just doing this for the sake of brevity. So suppose I give you the sum of I is equal to 1 up to n. Notice it's not k anymore, it's n, which isn't a constant. We're going to consider n log base b of n to the power of I, like before, except now I'm just going to replace the k with an n. We're going to try to prove that it's big O of a something. So we're going to find out what the something is. So the question is it still going to be log base b of n? So that's the real question at hand. So let's see. So the proof, we'll have the same kind of sketch as before. So just for the sake of brevity, I'm going to omit the setup for the proof because it is exactly the same as I had just over here. Just the exception is that you have it where instead of it being a k, it's an n right there. That's the only difference. Okay. So what I'm going to do now, you might say, okay, so Dan, what are you going to do here? Well, let's try to attempt to prove using the same technique we had before. Just before we actually get to the actual proof, because like I said, I don't want to get into those nitty-gritties quite yet. I want to convince you that the fact that that exponent is a constant actually really matters. So if I were to use the same approach over there, what would I pick as the constant? I would pick the sum, right? So in this case, I would pick c is equal to 1 plus 2 plus 3 plus all the way up to n, right? That's what we did last time, which based on the fact it's an arithmetic series, a finite arithmetic series, this should equal n times n plus 1 over 2. And we should be able to pick n0 is equal to 1. Are there any issues with these selections of these two constants? Because remember, if I pick those two constants, is there anything I'm doing here that actually is wrong? Because this most certainly will satisfy the inequality for all n is greater or equal to n0, right? Is there any false presumption I'm making? What's the error I'm making? There's got to be something up that's a little bit weird here, because you think that if this is the case, then it should be that this is log base b of n, right? Like that should be, I should be able to accomplish that. What's the error I'm making? Because that most certainly does not make a whole lot of sense if you actually think about it, because I'm adding this. Keep in mind, one of the terms in here is log base b of n to the power of n. And if you know the power rule, it's n times log base b of n, which that does not sound like something that would be log base b of n all by itself, right? Yeah, this is the error right here. Notice that this selection of the constant is actually not a constant. This is not a constant anymore. Do you see that? Because it depends on n. So you have to be very careful when you're setting up some of these proofs to make sure that you're in fact picking a constant. So you got to make sure you clearly identify what is a constant versus what isn't a constant. K is a constant, so we can use it. Just like in previous exercises before, we talked about how we can like pick, for example, like 2 to the power of k, where k was a constant. That's a rather big number if k is rather big, but it's still a constant. But the point is that this is not a constant. That's not constant. So we cannot use this approach. It breaks apart. We need something a little bit more. In fact, if we wanted to attempt to prove this, it would be flat out wrong because it's just not true. And this is actually one way you can easily see why that mistake happens. Like I said, the last term in that sum is log base b of n to the power of n, which this is equal to n times log base b of n. Which, this looks more like n log n, right? It looks more like n log n. But would n log n cut it, though? That's a real good question. Would n log n cut it? Well, let's look back at this. So if I were to attempt to use an approach kind of like this before, I might have to be a bit more careful, though. So if I just go n log n, notice I have 1 plus 2 plus 3 plus 4 plus 5, all the way up to n minus 1, many log base b of n terms, right? But it all depends on n as well. It might be a little trickier to do it. I'll let you think about if it's true or not. Instead, we're going to prove something that would be much more in line with what we did over here. So I'm getting very excited. So notice that I have n times n plus 1 over 2, but this is just n squared plus n over 2, or 1/2 times n squared plus n, which this is quadratic, right? So if you look at this and you want to adapt this technique, you would see that this should probably be something that looks like this, right? Not just log base b of n. That's at least one thing that I'll bring up here. So the same setup for the proof with the exception. So I'm just going to, we say that we have find the constant such that for all n greater or equal to n0, this sum is less than or equal. So this is less than or equal to c times n squared log base b of n. And you might say, Dan, what should I pick for the constant then? Well, let's think about it. If you apply the power rule, for logarithms, you'll end up with something that looks kind of like this times log base b of n, right? But you'll notice right away that this should remind you of something else that we were playing around with. Well, let's see, remember that's halving it. Well, what I'm going to do is I'm going to try picking c is equal to 1, and you're going to see how I might come about this. Actually, let me give you an intuition behind it. Well, you know that this is 1, 2, 3, 4, 5, 6, all the way up to n, right? Well, what if I made it so every single time it's just n here? Like there's n in there everywhere. Like instead of it just being 1, I'll put n there. Well, how many of them are there? There's n many of them. So n times n many of them, that should look like something like n squared. So that's where I'm going to go with this. I'm going to pick c is equal to 1. I'm going to try bounding it, making a good upper bound guess on what it would be. In this case, I'm going to kind of overestimate it. Instead of being I, I'm going to replace that with n. Because that most certainly will be a greater than I, given that's the highest value this sum will allow for any one summoned term. Well, one term of that sum in there for the summation. Pick c is equal to 1. Then we identify n0. N0. So that the sum from I is equal to 1 to n of log base b of n to the power of I is less than or equal to n squared log base b of n. So notice because I pick c is equal to 1. And this has to be, remember, don't forget this part, for all n greater or equal to n0. We have to have our quantifier in place. I don't want to omit any of them. So now we have this. Now what I'm going to do is I'm just going to simply apply the power rule of logarithms, and we're going to bound accordingly, okay? So we're going to apply the power rule of logarithms. Then starting on the left-hand side, so I'm going to start on the left-hand side, I'm going to derive the right-hand side, okay? That's what the strategy I'm going to use to show you that this is true for some values of n. So then starting on the left-hand side of this inequality, we have the sum from I is equal to 1 to n of log base b of n to the power of I. Well, this is equal to, like we had before, I'm just going to pull that exponent out front inside of the summand. So I have I times log base b of n. Well, this has to be less than or equal, I'm just going to overestimate now. So I'm going to have I is equal to 1 to n of n times log base b of n, right? But how many of them are there? There's n of them. So it's n times n log base b of n, which is just n squared log base b of n. And this is for all n greater or equal to 1, right? So what should I pick for n0 then? So notice that's the right-hand side. Well, I should pick n0 is equal to 1. Choose n0 is equal to 1. Thus, by the definition of big O, the sum from I is equal to 1 to n of log base b of n to the power of I is in fact big O of n squared log base b of n. And we're done. So just the main thing I really want you to take away is the behavior of exponentiation inside of a logarithm. Notice that in this case, we pushed it even further with having a sum like this. So just keep in mind that when it's a constant inside of here, it usually reduces back down to log. Those usually get eliminated. However, if it's involving n, the input of the function, that may not be the case, as we've seen in our examples. But yeah, so that's our example here for this one here. So now we've seen how exponents behave inside of a logarithm. Just give you a good flavor for how that works. Now, the next thing we're going to do here, I'm getting really excited. I'm not like a kid in a candy store at the moment. I'm just looking at all the fun things we have here to play around with. There's kind of like two things we can really play around with here. Well, let's think about this. There's a lot of things we can play around with. The next thing I was thinking about is maybe we're going to try doing is we're going to try proving that the base of the logarithm actually really doesn't matter. So very often in computer science circles, we presume that the base of the logarithm is always 2, but it doesn't have to be. In fact, there's another good reason why if ever you see somebody write big O of log n, like say they write big O of log n like this. Often what they actually mean is that there's a base 2 right there. But the point is, what the next thing we're going to see is that it actually really doesn't matter. That even if you presumed or not that it is a 2 there, it doesn't make any difference. So if I write big O of log n, it doesn't matter if it's a 3, a 5, a 2, it doesn't matter at all. That's also another reason why you'll find very seldomly that people write in big O notation the base of the exponent, unless it's just to be helpful for the reader to see where it came from. At least this is one way I can justify this for you. So I'm just going to take a peek and see what everything's going on over here before we get into our next example. Just taking a peek just to make sure we're doing okay. Yeah, today is a little bit more basic. But I will tell you up front that these are those little things that I'm not even kidding. If you have a poor computer science professor, if they aren't doing a very good job of illustrating mathematical review for you, or they focus on the wrong things pedagogically, some of these things are very easy things to fall into as a trap. This is just my 2 cents on the matter. I've seen it where some profs just straight up just focus on like laying out these functions from least to most dominant, and sometimes it's hard to have an intuition around, like if you give me sums like these, how they behave. And if prof doesn't really show you much about like how they might interrelate with each other, you might run into some trouble. As we've seen with the exponents and how they behave when they're a constant versus not being a constant. So just keep that in mind. So I'm just going to erase the board, and then we're going to get into our next examples. So the next kind of main part we're going to talk about is how we can talk about any arbitrary base in relation to another one. And it actually just simply uses a property that we have for logarithms called the change of base formula. It's a very important formula if you ever want to go from one base of a logarithm to another base. You want to switch the base. So we're going to talk about that. And then on top of that, we're going to talk about how we can come up with a proof that tells us how we can go from one base to another base in terms of big O. So that really, at the end of the day, it doesn't matter. It doesn't matter if you have log base 5 of n, or log base 10 of n, or log base 2 of n. It's just log n, like it doesn't really matter. You can have your audience presume it's base 2 or base at 64 if you wanted to. It doesn't matter in the big O. And we're going to see that actually towards the end of our session today, we're also going to see some of the more fundamental ones, relationships we have. For example, how we can get, how we prove that log base, well, one way you can prove that log base 2 of n is big O of n. So we're going to see that as well here today. And then also show you how you can show using just one presumption that I'm not going to prove here for you, how you can show that any one logarithmic function is always going to get dominated by any one polynomial. Now, you can come up with this quite quickly by using the transitive property from another session. Like, you know how I showed you how you can bridge complexity functions? So I already showed you that n to the power of k, where k is an integer, plus epsilon for some positive real number is in fact going to be big O. Sorry, n to the power of k is big O of n to the power of k plus epsilon, where epsilon is a positive real number. Well, if you think about it, if I give you something that looks like that, and I know that log base 2 of n is big O of n, well, what I could do is I can use that property to get any one of the ones later, right? I can go, like, if I want to know that log base 2 of n is big O of, say, 1.5, again, n to the 1.5. Or say, for example, I want to know it's n squared, not just n. You can use that property, but I think I want to show you another way you can come up with this under a presumption that you can probably derive from calculus. But I'll be taking only one basic fact to make this work. And it's one that I hope that will be reasonable for you to accept from me. Because it takes a much more general approach. It isn't just simply integers. It extends to real numbers. But it's something that you can convince most students of. If you need to pull out some calculus. But I'm not going to do that. Because we're focusing on just that approach. Just specifically what we're talking about in terms of big O. So, anyways, why don't we get into our next part here? I'm just going to grab another marker here just to make sure I've got enough good markers. Because I always have markers, but sometimes I find that I go through them quite quickly. So let me just grab one. So if I'm off scene, if you hear weird noises, it's just me grabbing a marker. Okay. So let's get in on this. Yeah. Other than that, before I get started, I just want to make a remark that the grouping of logarithmic terms with an exponent isn't the same as applying it when the exponent's within the logarithm. I should make that acknowledgement. So I'll have some remarks about that in the notes. Just be careful about that. So anyways, next we're going to talk about a relationship that logarithms have between bases. In particular, my goal here today is to show you that the base and the exponent actually doesn't matter inside of big O. In particular, when it's like, if it's a fixed number, it doesn't matter at all. So very often in computer science, we presume the base is base 2, but it doesn't matter. That's the goal here. I'm going to show you how you can actually prove this. So to do this, I need to get to talking about a lovely property that logarithms have. We're going to prove that, and then we're going to get into our big O proof. So I'm going to give you a well-known property. That R got really excited. A well-known property. It's called the change of base formula. The change of base, the change of base. And it works like this. And I'm going to assume that you're using valid bases for the logarithm. So for example, previously we discussed how 1 isn't a valid base for a logarithm. So if I give you log base a of x, this is the same as writing log base b of x divided by log base b of a. So using this formula, you can always convert from one base to another base. One thing I want you to take note of is that log base b of a, if a and b are fixed, so they're two numbers that are constants, notice that this will just be some 1 over this is just some constant. So just be mindful about that. Now, next, let's prove this. So we're going to use the definition of a logarithm. So just something helpful for us to remember is that if I give you something like log base a of x, so just keep in mind that log base a of x, suppose this is equal to y, This is no different than me writing, so this is if this is true, then it has to be that a to the y is equal to x. So just keep that in mind. That's from the definition of a logarithm. So just keep that in mind. So by invoking the definition of a logarithm, if log base a of x is equal to y, then a to the y is equal to x. See, I told you. So we have this at our disposal. So we're going to take logarithms of base b to both sides of this equation. So we're going to take taking logs to both sides of the equation. Equation a to the y is equal to x. That means that log base b of a to the y is equal to log base b of x. So next I'm going to use the power rule or power law of logarithms. Next, by the power rule of logarithms, we have that log base b of a to the y is equal to y log base b of a. So we get the following. So now watch this. Watch this. This is going to be me like the magician revealing the bunny out of the hat. So watch this. So that means that so I'm just going to kind of recap all of this. Log base b of a to the y is equal to log base b of x, which is no different than me writing. So this is an if and only if. It's a bidirectional. It's the same thing as me writing if and only if for our discussion. If and only if y log base b of a, because remember I'm just applying the power rule, is equal to log base b of x, right? But here's the thing. What's y? It's log base a of x, right? And we know y is equal to log base a of x, implying the following. Implying that log base a of x times log base b of a is equal to log base b of x. Pretty slick, right? But now we just finalize this. So we divide both sides of the equation by log base b of a, and then we're done. So I would recommend you write the statement saying that you're dividing both sides of the equation, this one, by log base b of a. But I'll just shortcut this with an implication arrow, which this is the same as me writing log base b. Well, at least this is an implication, so I can write this as a consequence. Log base a of x is equal to log base b of x over log base b of a, which is what we sought to prove, right? And we're done. I would recommend you have a conclusion. But yeah, so this gives you the proof for the change of base formula. So this is one way you can prove that. And now next what we're going to do is we're going to see how we can use this change of base formula to connect up any one logarithmic base. So if I write something in terms of logarithm with a given base, I can always go to log base 2 if I wanted to. Or I could just do it with any other base. Now, I must stress that the one thing I need to point out about this proof is that it presumes the bases are all greater than 1. But I must stress that if you fix one of the bases, there's more pliability. So like if you fixed one to be like log base 2 of n, it's a little more pliable. So just keep that in mind. But for most purposes you would ever want to use this, this will work. So anyways, so assuming valid bases A, B, and they're going to be greater than 1, both of them, for this proof. Just because of the way A and B interact in this proof, I have to make them greater than 1. But there's ways you could go around this, and you must stress that then you have a lot of different edge cases, and I'd rather that you focus on these ones, because these are the ones that actually matter when we talk about this property I discussed at the beginning of this lesson. So this is going to be the thing that gets you from proving that log base 2 of n is log base 3 of n, or like, sorry, big O of log base 10 of n, or the natural log. Like this is one way you could get this very quickly. So we're going to prove that log base A of n is big O of log base B of n. And it's all based around the fact that, like what we observed earlier, that what it does is it creates a multiplicative constant that I can use. So that change of base formula is going to be our best friend for doing this. So as per usual, I need to lay out the game plan. So I got to let the reader know what we're doing. We find constants. C, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, log base A of n is less than or equal to C times log base B of n. So now I'm going to apply the change of base formula. So watch this. Observe by the change of base formula the change of base formula, we get the following. That log base A of n is equal to log base B of n over log base B of A. Right? That's what the change of base formula we had over there would give you. So this is how we're going to go to from log base A to log base B. But you're going to notice very quickly that I have something that looks like 1 over log base B of A. So one thing we have to be very mindful of is what happens when B and A interrelate with each other. So just that's why I'm keep in mind that that's one of the main reasons why I am picking the A and B like this. But I'll let you think about it. If you have any ideas, let me know. So what I'm going to do is I'm going to pick C to be equal to 1 over log base B of A. So ideally I would like to just put this as a multiplicative constant, then I just get this, right? I'm just trying to make it look a lot like the left-hand side is like the right-hand side. So I picked C like this, then notice you could notice that log base A of n is less than or equal to 1 over log base B of A times log base B of n, which this right here is just simply equal to this, right? It's just the ratio of these two things. Log base B of n over log base B of A, right? That's what this means. But notice that this is like, if I have this, right? Then I said it is this, but what's this? Well, that's just the left-hand side, right? This is log base A of n. I know it's a little bit of a fun ride there. That's quite the roller coaster. Then I'm just going to choose n0 is equal to 1. And then we have therefore, by the definition of big O, big O log base A of n is big O of log base B of n. And that completes the proof. So you might ask, Dan, why did you pick the constants the way you did in the claim? Well, if you look carefully at this, I need 1 over log base B of A to be a positive constant. So one thing you have to be very mindful about is that if you pick the constants where they are allowed to be smaller, then sometimes B and A interact in a way that may not be ideal. I encourage you to think about this, but most certainly there's other ways you can go about this. If you fix, say, for example, one of them, say, for example, if B was 2, for example. If you make B 2, then there's more things you could play around with. But I wanted to give you just an idea of how you can go from one base to another base with the big O. And this is very often, like I said, in computer science, we often think of the base as just 2, but so it's often, it's not even written, it's just presumed. But also from a mathematical standpoint, that rated M word, the mayonnaise or mustard, the big thing I'm getting at is that the B, like the fact that you can always re-express it in a different base that's an integer base that's larger than 1, right? That's the big point here. But this should hopefully give you some context for how this gets often glossed over. So hopefully you found that interesting. So anyways, the next thing I would like to talk about is a very nice classic idea of how you can relate logarithms with linear functions. So the next thing we're going to do is we're going to try proving that log base 2 of n is big O of n. So you might say, Dan, that just sort of it's obvious. But it isn't, it shouldn't be obvious. You should have some reason or way to verify this for somebody. There's a lot of ways you can do it. I'm going to show you one way. So this is a much more discrete way of going about it. But at the heart of this claim is going to be the following. It's going to be that we're going to try showing that for every integer n greater or equal to 1, that log base 2 of n is less than or equal to n. So that's what we're going to try proving. And once we have this, then we can prove quite easily, right, that log base 2 of n is big O of n. Because if it's true for all n greater or equal to 1, you just make c is equal to 1 and n0 is equal to 1 and you're done, right? So I'm going to erase the boards here, and then we're going to be getting into that. The way we're going to achieve this is using mathematical induction. And we're going to use our properties of logarithms to help us establish these claims. So, and one other detail I wanted to bring up is that once we have that log base 2 of n is big O of n, we can also flip this. Like, you know how we talk about logarithms or invert, like, the inverse of a logarithm is an exponent, right? And vice versa. But keep in mind, sorry, I should say that the inverse operation of exponentiation is a logarithm, right? So that means that if I talk about this, that means that now I have a way of bridging from like, say, something that is like linear to exponential. So I have actually a bridge now that I can use to get there from a logarithm to linear. So now I can use that as a bridge to get to exponential functions and using those as approaches as well. So the idea is that you just simply take logarithms to both sides, then now you have something in relation to logarithms all of a sudden, right? And that's kind of your best friend after this point. And then that'll leave us with one last thing after that, where we're going to show that log base 2 of n is always big O of n to the epsilon for any one positive real constant, which the proof is surprisingly simple. It's just that you have to be careful because it works under the presumption that, like, and keep in mind, the backbone of this proof is knowing that log base 2 of x for any positive x, it has to be that is less than n. Sorry, less than x. Sorry, I'm getting my variables crossed up because we're having a little bit of fun here. But yeah, so that's kind of the roadmap for the rest of the session. So I'm just going to grab a little water here, just because it's probably a good idea to do that before I get into this too deeply. Where did I put my water? Here it is. I found it. I'm somewhere in the dark, way off scene. So yeah, I found my water bottle. So as per usual, if you find yourself very fascinated by a lot of what we're talking about here, I recommend you check out the Patreon. Go patreon.com/pagewizard or pagewizardgames.com for more information. In addition, of course, make sure you subscribe. Tell your friends to come on out. I'm giving you some of the ultimate guide tools for dealing with this topic. So, for example, if you're taking a data structures and algorithms class, I'm giving you a lot of the core techniques that are going to help you succeed in a class like that. Especially when you talk about Big O, because very commonly I find that students this tends to be one of those first real topics that you tend to encounter that has formal aspects to it. Usually this becomes more common in computer science as you go up, but most certainly it's one of the first things you really kind of run into. It's like, oh, it's a formal definition. What am I supposed to do with this? So you'll find that a lot of what we're doing here will help ease that process. So whether you're interested in a topic or maybe you're taking a class in this, you're going to find that a lot of the tools I'm giving you will help you beat the tricks of your profs, okay? So, or at least it'll give you a lot of things that maybe you don't have all the time in the world to talk about during class time. So I'm just going to erase the boards here, and then we're going to get to our next part here. Because once we get this, then we actually have a lot of the core things when it comes to relating some of our complexity functions. Because we talked about polynomials, we've talked about like constants, we've talked about logarithms, we've actually even talked just now about n log n, for example, how that might pop up. We talked about, but we haven't talked about exponentials, and nor have we talked really about how they bridge to logarithms and so on. So this next bit's rather important for bridging those two concepts. So, anyways, let me just, my glasses, they're sort of falling into each other. Oh man, that's some good stuff. So let's, anyways, let's get into the next part here. Okay, everybody? So anyways, today we're going to be focusing in on a classic claim. I would like to be able to prove to you that log base b of n is big O of n. Now you might say, Dan, that's kind of obvious. How do I know? That should be just obvious. It's easy. Well, it's important that I give you at least one way to get there, okay? So a key ingredient to make this proof work is I'm going to prove the following claim for you. So for every integer n greater or equal to 1, it has to be that log base 2 of n is less than or equal to n. Now I must stress that there is a stronger claim you can make here, but this is all I need to make this work, okay? So to do this, I'm going to use mathematical induction. So I'm going to use the principle of mathematical induction to make this work. So I'm going to formulate this in terms of an induction proof. Now I've talked about induction before, so I'm hoping that you'll catch on pretty quickly what we're doing here. So I'll remind you as we're going along. So this is the statement. I'm going to reformulate it in the following way. For each integer n greater or equal to 1, let L of n denote the statement as follows. So L of n is log base 2 of n is less than or equal to n. So What I need to do is prove this for all n greater or equal to 1. If we could do that, we win. We won. We've proven the claim. So I formalize the statement. So first thing I do in an induction proof is I work with the base step. So I got to start with the simplest, the first several inputs. Now in this case, I should be good enough just doing n is equal to 1 because my statement only, like the way I'm going to perform the induction only relies on the previous statement, like the one less input, not 2 or 3 beyond that. It should be just rather straightforward. So the base step here, this is when n is equal to 1, is as follows. For L of 1, so L of 1, so we're going to prove L of 1 is true. The statement log base 2 of 1 is less than or equal to 1 is true as log base 2 of 1. Okay, let's think about what log base 2 of 1 would be. Okay, if I have 2 to the something is equal to 1, what's the exponent have to be? What does it have to be? It has to be 0. So let's make it, so this is equal to 0, which is in fact less than or equal to 1, right? So that's the base step. Now, to get the induction step working, what I'm going to do is I'm going to show, given L of k, I want to show that L of k plus 1 also holds. So if I assume L of k holds, then L of k plus 1 must follow from it. So just as a reminder, the way this works, say if I think about Miss Kitty and I'm trying to teach Miss Kitty how to climb up to her bed, say it's on a bunk bed, I need to show, so I start off at the bottom rung. I've shown Miss Kitty how to get to the first rung through L of 1. Now what I need to do is I need to show for an arbitrary rung of the ladder how to get Miss Kitty up to the next rung. So how do I prove, given that L of 1 is true, how do I show that L of 2 is true? So the goal here is I'm going to try to reformulate L of 2 so that so I can use L of 1, which I know is true. And the idea is that if I pick any arbitrary rung, I can take L of 2 to show that L of 3 is true. Then L of 3 is true, then L of 4 is true. Or say L of k is true, then L of k plus 1 has to be true. And just like, if you imagine it's like I'm knocking off some dominoes, it's a whole row of these suite going all the way across for all integers greater or equal to 1. If we use the principle of mathematical induction. So that's how the principle of mathematical induction will get used here. So here's the induction step, or the inductive step. I'm going to show that if L of k, then L of k plus 1. So I'm going to fix some integer k plus 1. Sorry, not k plus 1. K is greater or equal to 1. So I'm going to fix for one rung. So for one given rung, I'm going to fix k greater or equal to 1. And I'm going to assume L of k, which, as a reminder, that's at log base 2 of k is less than or equal to k. So this is going to be our induction hypothesis, or inductive hypothesis, is true. We prove next that L of k plus 1 follows, which, remember, L of k plus 1 is at log base 2 of k plus 1 is less than or equal to k plus 1. That's what L of k plus 1 is. We have to show that this follows. So what we're going to do is we're going to start on the left-hand side. So we're going to start on the left-hand side of L of k plus 1. And I'm going to take advantage of the fact that I can bound the inside of this, so the input here. So k plus 1, I'm going to bound this from above with a product. I've done a technique kind of like this before in another lesson before, but check this out. And once I have that, then I'm going to use properties of logarithms. So beginning with the left-hand side of the inequality, we can say log base 2 of k plus 1 log base 2 of k plus 1 is what? Well, what I ideally would like to have is something that looks like L of k. So I want to make something that looks like L of k. So something involving log base 2 of k. If I can get that, then we're in good company. So this, my claim is that this is less than or equal to log base 2 of 2k. Now, if you're not convinced by this, let's just kind of work it out on the side here. Well, now remember, what I'm really saying, because logarithms are increasing functions, I have to really just compare the inputs in here. I have to show that k plus 1 is in fact less than or equal to 2k. If I can do that, then log base 2 of k plus 1 has to be less than or equal to log base 2 of 2k. So k plus 1, suppose that I have k plus 1 is less than or equal to 2k for all k's greater or equal to 1. So suppose I have this. This has to be true if and only if the following is true. Well, let's see. I have the following. Well, let's see. I can subtract off k from both sides, so I subtract k from both sides. And now I end up with 1 is less than or equal to k. And do you see how this is just saying that this has to be true for k is greater or equal to 1, right? That's what all it's saying. So that's what I'm saying, is that this is true because of this. So this is guaranteeing that this holds for all k is greater or equal to 1. Well, next, this is equal to this. So I'm just going to rewrite this in a deliberate manner. Log base 2 of k times 2 inside the input here. So for the input. But next, I'm going to apply the product rule of logarithms. So log base 2 of k plus, so I'm just going to split this into two sums. Log base 2 of 2. So this is the product rule of logarithms. That made me possible to do this. It's not magic, it's just math. So let's do this. It's that math, okay? But what's log base 2 of 2? Okay, 2 to the what is equal to 2. What is that? 2 to the power of what is equal to 2? Just 1. And this is just 1 here. So look at this. So this is just log base 2 of k plus 1. But here's the thing. What's this? That's the left-hand side of L of k, right? But we know that that's less than or equal to k, right? So this is by the induction hypothesis. And you see that we just showed, using the induction hypothesis, we got from L of k to L of k plus 1. Because, which is the right-hand side, right, of L of k plus 1. Thus, L of k plus 1 holds. So it also holds. Therefore, we can use the principle of mathematical induction, because we have all the pieces and pieces. By the principle of mathematical induction, which I'll abbreviate as principle of mathematical induction as PMI, L of n is true for all n greater or equal to 1. And we're done. So now we know for all n greater or equal to 1 that log base 2 of n is less than or equal to n, which is all we need as the key ingredient, right? Because you actually think about it, if I wanted to prove that log base 2 of n is in fact big O of n, well, now I told you that for all n greater or equal to 1, this is true, right? So I can pick n0 to be 1, and I can pick c to be 1, and that's it. It's a piece of cake, right? So let's now prove it. So let's actually put this all together now. So I'll show you this, and then I'll show you a nice way you can apply this result. So you can apply this result we just showed over here. So the next thing we're going to do is we're going to prove that log base 2 of n is big O of n. So this is a nice, pretty, I would consider it a rather important relationship that logarithmic functions have with linear functions. So we have to do what we usually do. We need to lay out the game plan. To prove the claim, I was about to say, to prove the claim, we find constants. C, which is a positive real number, and n0, which is a positive integer. Such that log base 2 of n is less than or equal to c times n for all n greater or equal to n0. So, like I said, I'm just going to pick c is equal to 1. And then observe by the previous theorem that log base 2 of n is less than or equal to n for all n greater or equal to 1, right? Pretty wonderful, right? So we have all the key ingredients. So now I can just simply choose n0 is equal to 1. Therefore, by the definition of big O, we have that log base 2 of n is big O of n. And we've established this nice classic property. That's pretty wonderful, right? So we've sorted that out. So now we know that log base 2 of n is big O of n. And I must stress that this proof is not very hard to modify for arbitrary other bases, because the way the proof worked before is not that much different. So notice that the way I did things with the base didn't really matter a whole lot, right? So anyways, next thing I would like to talk about is a basic application of the following results. So like what we just talked about here. So the next thing I want to do is I want to prove to you that n is big O of 2 to the power of n. So I would like to bridge those two. So next we're going to prove the following. So next we're going to prove that n is big O of 2 to the power of n. You're going to see that I already have all the machinery to make this work. So watch how slick this gets. So we just got to find the constants, right? We find the constants c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, n is less than or equal to c times 2 to the power of n. I'm just going to pick c is equal to 1, and we're going to proceed in a way that should remind you of something. Pick c is equal to 1. We're going to apply logarithms to both sides. Of the inequality. both sides of the inequality. Then we find n0 so that log base 2 of n is less than or equal to log base 2 of 2 to the power of n. What's this? Well, the power rule says you can pull this n out front, and then we have log base 2 of 2, which is equal to 1, right? This has to be found such that it's true for all n greater or equal to n0. But look, we already proved this, right? We already know that log base 2 of n is less than or equal to n for all n is greater or equal to 1. So let's just say that. By the above property, log base 2 of n is less than or equal to n for all n greater or equal to 1. So choose n0 is equal to 1. There. Now we got the two constants. Therefore, by the definition of big O, n is big O of 2 to the power of n. Piece of cake, right? It's just a direct application of that proof we got, of our claim that we proved with mathematical induction. Is that wonderful? So now we have a way we could bridge to the exponential functions by just simply using this very basic claim. So I think the best place to go next with this is see what we could do with exponential functions. Now that we have 2 to the power of n, I would like to be able to say something about 3 to the power of n or some arbitrary powers of n. So I want to kind of come up with a cookbook way of dealing with this. So I go from like 2 to the power of n to say 5 to the power of n, or some arbitrary L to the power of n to U power of n. So that's going to be the next thing we're going to do here. So let's take a look at this. So you're going to see that the bits and pieces that make this claim work for our first basic example are actually going to be very easy to generalize. So I want you to take note of the fact that sometimes things only being 2 or 3 or 4 may not actually matter. The technique might actually be a little bit more general than just that. So we're going to try proving that 2 to the power of n is big O of 3 to the power of n. So as per usual, we need to lay out our game plan for how we would do this. So we find constants. We find constants. We find constants C and n0, which is a positive integer, right? Such that for all n greater or equal to n0, I had to kind of squish it in there. For all n greater or equal to n0, 2 to the power of n is less than or equal to c times 3 to the power of n. So we've seen when we deal with exponentials that we can actually apply logarithms to both sides of these inequalities. Well, let's try doing that here. Now I have a 2 here and I have a 3 here, and I know that exponential functions like these are increasing functions. So if I have a 2 here and I have a 3 here, notice that 2 raised to something, at least the intuition behind this should be less than the 3 to the something, because every time I increase n, it always makes this side while it goes up, it doesn't go as fast up as the 3 to the power of n. So we're going to pick c is equal to 1. Then what we're going to do is we're going to take logarithms to both sides of the inequality. So now what we have to do is find the n0. we find n0 where log base 2 of 2 to the power of n is less than or equal to log base 2 of 1 times 3 to the power of n, which this has to be for all n greater or equal to n0, right? Well, here's the thing. Remember the power rule of logarithms? So remember, I could pull this n out front. Notice that this one, it's 1 times that, so I could just rewrite this as this. So this is just n times log base 2 of 2. And this is just n times log base 2 of 3. But here's the thing. What's log base 2 of 2? That's equal to 1, right? But what's this? This is because log is an increasing function. So log base 2 of 3 has to be greater than 1. So it's greater than 1. So I have n is less than or equal to n times something slightly bigger than 1. So that most certainly doesn't make it smaller, it gets bigger, right? So that means that we can use this fact right away. So notice that log base 2 of 2 is equal to 1, which is less than log base 2 of 3. And this is because logarithm is an increasing function. So for all n greater or equal to 1, n times log base 2 of 2 is equal to n, which is less than or equal to n times log base 2 of 3. So we're just going to simply choose n0 is equal to 1, and then we're done, right? Well, we're not quite done, right? We still have to invoke the definition of big O. Because now we have the two constants I can present to somebody. So let's do that. So therefore, by the definition of big O, to the power of n is big O of 3 to the power of n. Okay, so now we know that 2 to the power of n is big O of 3 to the power of n. Wonderful, right? Now you might be staring at this and saying, Dan, there's a lot of stuff here akin to some of the previous things we've talked about, like the idea of how we could generalize our ideas. Can we generalize this claim even further so we can say more about exponential functions? So what I want to do is I'm going to presume that we have two positive reals, L and U. Let positive reals, L and U, exist so that, oh yeah, they also have to be greater than 1. That's another catch with this. Because remember, if we're trying to apply logarithms, we want to be very careful. We want to make sure that we're just going to be careful here. Now, there's more things you could say potentially, but this is what I'm going to restrict things to. I think this is a pretty nice basic generalization. So L and U are greater than 1, where L is less than or equal to U. So what I want to do is I want to take this, and we're going to try generalizing this proof so that it's not just 2, it's L. L to the n is big O of U to the n. So I would like to generalize our ideas here. So let's walk through what we have here on the board, and let's see if we can generalize our ideas. So we have the two constants, right? That's all okay. So I'm just going to replace the 2 and the 3 with L and U. So far, the reasoning seems pretty clear so far. We haven't deviated from the claim up above. And what we're going to do is we're going to still pick C is equal to 1, because remember, L is less than or equal to U. And if we keep the intuition we had last time about 2 versus 3, it should extend for anything that is 1 where L is less than or equal to U, right? Because of the nature of exponentiation being increasing functions, but also logarithms being increasing functions too, right? At least the way that they're going to manifest themselves in the way we play around with this. So pick c is equal to 1, then we take logarithms on both sides, so we find n0 such that where L to the n is less than or equal to 1 times u to the n. If we play around with this, we end up with log base something. Now, I'm going to set the base to be L. Why? Because then I have log base, so I have n times log base L of L, which will equal, what does that equal? It equals 1, right? So I'm trying to come up with a way to kind of generalize this. So if I take base, I have to take the same bases to both sides because of the way we're playing around with this. I already had some discussion about this earlier, right? So I have this, and we know, so we can notice the following. We could say log base n, log base, not L, not n, not 2, not n, but L of L is equal to 1, but this has to be less than log base L of u. This is because L is less than or equal to u, right? So, for all n greater or equal to 1, n times log base L of L is equal to n, because it's just 1, right? And then we have that's less than or equal to n times log base L of u. Which this has to be strictly greater than 1, right? If L is in fact less than u, but if they're equal, this should be an equality, not an inequality necessarily. So we get this for all n is greater or equal to 1. Oh, yeah. So we got this, that's wonderful. And that looks like we're in pretty hunky-dory mode, right? So we can choose n0 is equal to 1. Then we can say, therefore, by the definition of big O, L to the n is big O of u to the n. And we're done. I forgot my fun box to finish off the proof. So notice that now we have a much more general proof that tells us relationships between different exponents in terms of big O. Pretty slick, right? But all at the heart of this is just simply taking logarithms to both sides. Now, the main thing I need to warn you about this is that we're still using the logical branching from taking the logarithms of both sides because we presumed that the inputs of these functions originally would have been this way, right? We talked about this towards the beginning of the session. We have to be very careful if we were trying to make claims beyond this, which you may have been exposed to if you've ever taken a calculus class, especially if you're trying to find specific roots and things like that. Now you're talking about somewhat different functions. Here, it's okay, because we're talking about whether this statement, that statement is holding for all n is greater or equal to n0, and because we have this, then I'm going to take logs to both sides of it, and if that's less than or equal, in fact, then this has to also be the case. But anyways, that's just some diversion for me, okay? So my main point here is that we've seen a natural way of branching out our claim from before. Isn't that pretty cool? But yeah, well, it's a rather quiet day today. So anyways. So we've seen actually some plenty of examples here. We've seen how we can talk about exponentials now. We have talked about logarithms. I must stress that one thing I didn't bring up is that you can prove that n to the k is big O of 2 to the power of n. You could use a little bit of calculus to make that work, using a property that I haven't yet really discussed, at least at this point. There's a limit theorem for big O that you can employ, and you can use a limit to determine that is true or not. But there's other ways to prove it as well. But what I'm going to do next is I'm going to do one last example with you guys. And this one's all going to be anchored into the presumption that you know the log-based, like if I give you any input real x, log base 2 of x is less than x for all n greater or equal to 1. Sorry, for all x. that are greater or equal to 1. Sorry, my apologies. I'm getting very excited about this. Oh, I just about knocked my turtle friend. So we're going to try doing this last example, and I think this will be a perfect place for us to stop. There's more things I could talk about with logarithms. Maybe I will in the future talk about some of those. So let's get into our last example for today. So anyways, we're going to be considering this next claim here. And so to make this proof work, I'm going to assume that you are convinced sufficiently that log base 2 of x is less than x for all x that are positive real numbers. So I'm going to presume that this is in fact something that you're familiar with. Like, this is a true statement, but I'm just going to take this as a given. So I want to show you how you can use this claim akin to how we prove that log base 2 of n is big O of n. I would like to be able to show you something that's a little stronger of a claim. So here's the claim. That m is looking a little bit melted. For any real constant, epsilon, which is going to be greater than 0, it has to be that log base 2 of n is big O of n to the power of epsilon. So this means things like square root of 2, we're talking about like n squared, all of them. So every polynomial that's in here, like it means that the logarithmic function does not, if you want to put this in growth rate terms, it's saying that any logarithmic function will be eventually dominated by some polynomial of any exponent that is greater than 0. That's the claim. So this is one way you can justify to somebody that, oh, if you have an algorithm that runs in logarithmic time versus one that runs in polynomial time, well, if the exponent is not terribly big, but it's big enough that it might make a difference between choosing between a logarithmic one and say square root, like I say if it was log base 2 of n versus square root of n, you can use this to show that square root of n would be in fact something that would bound it eventually for a sufficient constant and sufficient value of n. So let's prove the claim. It's going to be rather nice and slick for us. So as per usual, we need to come up with a game plan here. To prove the claim, we compute constants. C, which is a positive real number, and n0, which is a positive integer, so that for all n greater or equal to n0, log base 2 of n is less than or equal to c times n to the power of epsilon. So what I'm going to do is, remember, epsilon is a constant, so I'm going to use it. So what I'm going to do is I'm going to try to make something that looks a little bit like the left-hand side, but I need to do a little bit more to make this work. So what I'm going to do is I'm going to pick the constant for you, and I'm hoping that you'll stick around with me for the ride. So I'm going to pick c is equal to 1 over epsilon. Then we find n0 so that log base 2 of n is less than or equal to 1 over epsilon times n to the epsilon for all n greater or equal to n0. Okay. So if I can make something that reminds you of this statement up here, then we're done. So if I can make something that works a lot like that, then we're done. So you'll notice that you might look at this and say, Dan, is that a positive real constant? Well, let's think about it. If it's some fractional number, like say if it's like 1 over pi or something, well, that's going to be some number that is less than 1, but most certainly it just makes this larger, right? 1 over something less than 1 will most certainly make this larger than 1. If it is, say, 1 or greater, then it's just going to be 1, or it's going to be, if it's greater than 1, then this is going to start being something that is going to be less than 1, but it's going to still be positive. So now we're going to use the power rule of logarithms in a following very cheeky kind of way. So watch this very carefully. So I'm going to manifest an exponent using properties of exponents. So watch this carefully. This is a little slick trick I'm going to pull on you. Notice by invoking the power rule of logarithms that we can rewrite log base 2 of n as follows. Log base 2 of n to the power of epsilon raised to the power of 1 over epsilon, right? Because remember, this will have it where it turns into a product, right? Epsilon times 1 over epsilon is just 1. But what's this? This is just simply 1 over epsilon times log base 2 of n to the power of epsilon. Interesting, right? That's interesting. So you're staring at this and you're like, okay, so what do you do? So what do you do with this? Okay. Well, let's go over to the other board here. Let's think about this. And you're going to see that when we have two things that we know are one is less than or equal to the other, that if I apply it to equally, like apply an operation to both of them equally, meaning that, say, for example, like we take logs of both sides or we exponentiate both sides as we're going to do here, that I should be able to maintain the same properties given the fact that exponentiation, if one thing is less than or equal to the other thing, then since it's an increasing function still, when I exponentiate, then it still has to be, if this is less than or equal to that, then the result of that has to be less than or equal. So now I'm going to use this fact that we have over here. Since log base 2 of x is less than x for all positive reals, then it has to be, by simple extension, then log base 2 of n to the epsilon is less than n to the epsilon for all n greater or equal to 1. Does everybody see what I did here? So remember, this is just the input of the logarithmic function. This is the input for what x would be. So you just put I'm just putting the same quantities into here. So because this is true, this has to follow, right? Because these are the same, like this is like, if you imagine x being n to the epsilon in both these cases, remember, epsilon is a constant, right? It's just taking whatever that number is and applying something, which will end up still being a positive real number, right? Because this is the much more general statement. So I'm just going to use it. And thus, so now we have this, and thus, for all n greater or equal to 1, we're going to now bridge it. Log base 2 of n is equal to 1 over epsilon times log base 2 of n to the power of epsilon, which we've established that this is less than or equal to 1 over epsilon times 1 over n to the epsilon, right? Because it's just 1 over epsilon there, and I'm just going to tack that on. Just going to hitch it for the ride. So now, I know this is true for all n is greater or equal to 1, so I'm just going to select n0 is equal to 1. Therefore, for all epsilon greater than 0, by the definition of big O, log base 2 of n is big O of n to the epsilon. So for you in plain language, this is saying that any logarithmic function of this sort is always going to be dominated eventually by any one polynomial of that form, n to the epsilon. So all of these belong to n to the epsilon regardless of what epsilon is. So for example, you get as a consequence of this, so a consequence as an example is that log base 2 of n is big O of square root of n. So if you have an algorithm that runs in square root of n, you know, if I gave you two algorithms, one where one runs in big O of log n, the other one runs in big O of square root of n, this is telling you right up that logarithmic function is going to be potentially faster than the square root of n. So for sufficiently large n. These are both, by the way, pretty slow moving, but most certainly the logarithm will grow much slower. But yeah, no, so isn't that pretty nice? So using a very basic property that you could derive, say, in a calculus class, you most certainly can come up with something quite slick like this. So, anyways, that's the last example I have here for today. And that's everything I have to say really about logarithms for now. I may come up with some more examples. I'm just trying to think of anything else that I may be missing. I think I got everything. Are there any questions out there? I'm really happy to answer any questions. Just don't be shy. I'm really happy to answer anything. It's a pretty quiet day today. But that's okay. It's okay. If you find yourself stumbling across this in the future, I encourage you to check it out. I will be, of course, taking the most important elements from this session, and they'll be broken into smaller, more digestible format for you to watch in the future. So if there aren't any questions, because I don't see any questions or anything, I'm going to stop right here. I want to say thank you so much. I'm going to just get my hat off. I've had enough of this for today. Although I love the hat. I love the hat. So that being said, what I was thinking of doing is I'm going to stop right here. I want to say thank you so much for coming and hanging on out with me. And I'll wish you a beautiful day. And I'll see you later.